Welcome to CS 1401 Video 14.1. In earlier videos, I presented iteration, which is a way to control the repetition of actions, or more informally, to handle loops. In this video, I'll introduce a very different way to write repeated actions, called recursion. A recursive function is a function that calls itself. Computer scientists love recursion, like car enthusiasts love drifting. Recursion is an elegant way to define looping behaviors and produces beautifully clean algorithms. The main idea is to have an algorithm call itself with successively simpler problems until the algorithm reaches a problem it can solve immediately. Before we look at a recursive algorithm, let's write an iterative algorithm to compute factorial. We recall that, by definition, factorial of 0 is 1, factorial of 1 is 1, and factorial of n is the product of the numbers from 1 to n. So, for example, factorial of 4 equals 1 times 2 times 3 times 4 equals 24. So here's an iterative algorithm for factorial. First, I'll initialize the result to be equal to 1, because that's going to be true for n equals 0 or n equals 1. And then if n is greater than 1, so I'll start with I equals 2, I'll make the result equal to our current result times I. And I'll do that as long as I is less than or equal to n. And each time I execute the loop body, I'll increment I. So by the time the loop finishes, result is going to be equal to the product of all the numbers from 2 to n. And we'll return that result. Now, let's develop a recursive version of factorial. I'm going to begin by noting that 1 times 2 times 3 times 4 can also be expressed as 4 times 3 times 2 times 1. This is going to be helpful because when designing recursive functions, we're going to need a convenient place to stop recursing. For factorial then, I note that fact of 4 equals 4 times 3 times 2 times 1, and that fact of 3 equals 3 times 2 times 1. This means that fact of 4 equals 4 times fact of 3. Indeed, in general, fact of n equals n times fact of n minus 1. As my function keeps decrementing n, its value will eventually reach 1, and because I know that fact of 1 equals 1, I have reached the function's base case and I can stop the recursion. Here's my recursive algorithm for fact. If n is less than 2, return 1, and that works because fact of 0 and fact of 1 are both equal to 1. That's my base case. Else, I return n, which is going to be 2 or greater, times fact of n minus 1. That's my recursive case. Wow, this is so clean. It's just basically the definition of factorial expressed as an algorithm. I want you to notice that this algorithm, like all recursive algorithms, has a base case and a recursive case. In fact, a recursive algorithm can have multiple base cases and multiple recursive cases, but it has to have at least one of each. Each time a function or procedure is called, or a method is called in Java, the system creates an activation record. An activation record is where the system holds the values for that particular call to the function. That is, if I call fact of 8, there's an activation record with n equals 8. And if fact of 8 calls fact of 7, then there's another activation record with, in that copy, n equals 7. To get the idea, let's trace the algorithm fact for n equals 3. For this example, I'll call fact of 3. It creates an activation record where n is equal to 3. And the first thing it's going to do is to check to see if n is less than 2. Well, in this case, n is not less than 2, so it will call fact of n minus 1 so that it can return n times fact of n minus 1. Well, fact of n minus 1 is fact of 3 minus 1, which is 2, so it will call fact of 2. When the activation record for fact of 2 gets created, the algorithm will check to see if the argument n is less than 2. Well, 2 is not less than 2, so it's going to go to the recursive case and try to return 2 times fact of 2 minus 1, or fact of 1. As a result, it calls fact of 1. Next, it checks to see if n, that is 1, is less than 2. Well, in this case, 1 is less than 2, so we've reached the base case, and it returns 1. So the current activation record will return the value 1 to the version, the copy of the algorithm that called it. So fact of 1 is now 1, and the call to fact of 2 is going to return 2 times fact of 1, which is 2. And now the original activation record, the original copy of the algorithm, can return 3 times fact of 2, which we know to be 2, so it returns 3 times 2, which is 6, and we're done. Here's another example of a recursive arithmetic function, calculating modulus, which is a fancy word for remainder. For example, 13 mod 10 is 3, and 7 mod 2 is 1. We used mod when we wrote the algorithm is even. Here I'm going to write the mod algorithm from scratch rather than use Java's built-in arithmetic operator. I remember that given two numbers n and m, the definition of mod is what's left over after subtracting m from n as many times as possible. For 13 mod 10, I can subtract 10 from 13 once, leaving a remainder of 3. For 7 mod 2, I can subtract 2 from 7, leaving 5. Subtract 2 again, leaving 3. Then subtract 2 just once more, leaving a remainder of 1. So here's my idea for the recursive function for n mod m. If n is less than m, return n. That's what's left over. If n is not less than m, then I subtract m from n and try again. Now, what happens if n is equal to m? So for instance, like 10 mod 10, well, I subtract 10 from 10 and get 0. So when I call n less than m, 0 will be less than 10, and I'll return 0, which is the right answer. Here's the pseudocode algorithm for this approach. The algorithm is called mod. It takes two arguments, n and m. If n is less than m, then return n, else return mod of n minus m and m. And each time it recursively calls mod, n will be decremented by m, and the problem becomes simpler and simpler until at some point n is less than m, and I'll reach my base case and return n. To see how this works, I'll trace the activation records. In this example, I'll call mod of 7.2 from the command line. That will create an activation record, a call to mod with 7.2. And the first thing it will do is check to see if n is less than m. Well, 7 is not less than 2, so we'll go to the recursive case, and the algorithm will call mod of n minus m, m. In this case, 7 minus 2 is 5. so it'll call mod of 5, 2. We'll create a new copy of the algorithm, 5, 2, and the first thing that will do is check to see if 5 is less than 2. Well, 5 is not less than 2, so we're not at the base case. Instead, we're at the recursive case, and it will return mod of n minus m, that is 5 minus 2, that's 3, so mod of 3, 2. And it calls the algorithm again. This time, mod of 3, 2, creating a new activation record. This time again, it'll check to see if n is less than m. Well, it's not, so it's going to call mod of 1, 2 this time, and create a new activation record for mod of 1, 2. This time, when we check to see if n is less than m, well, 1 is less than 2, so we've reached the base case, and it will return 1. So the value goes back from this activation record, this copy of the algorithm, to the copy that called it, and we return the value 1. So the value of mod 1 of 2 will be 1, and mod 2 of 3, therefore, will also return 1. Mod 3 of 2, the value of that is 1, so mod 5 of 2 will return 1. And similarly, mod 7 of 2, our original call, will also return 1, and the algorithm will return that on the command line as the result. The function to calculate the Fibonacci series is a natural for a recursive approach. Recall that the Fibonacci series starts 0, 1, and then each succeeding number is the sum of the two preceding numbers. So the Fibonacci series starts 0, 1, 1, 2, 3, 5, 8, 13, and so on. I'll start counting the series from 0. So fib of 0 is 0, fib of 1 is 1, fib of 2 is 1, and so on. Here's my recursive algorithm, fib of n. If n is less than 2, return n. Well, that works because fib of 0 is 0 and fib of 1 is 1. That's our base case, or rather our two base cases. Else, and here's a recursive case, I return fib of n minus 1 plus fib of n minus 2, because fib of n is equal to the two preceding values in the series. For fib, the algorithm is a direct expression of the definition of the function. And for n greater than or equal to 2, the recursive case, the function calls itself twice. As an exercise, try tracing the activation records for fib of 4. What happens if a subprogram doesn't return a value? In other words, what if the subprogram is a procedure rather than a function? To explore this, let's take a look at a really simple algorithm that, given an integer n, counts down on one line all of the numbers from n to 1, ending with a new line. For example, on the terminal command line, countdown 5 would print 5, 4, 3, 2, 1, and then a new line. My approach will be to realize that if n equals 0, all I have to do is print a new line, and I'm done. Now, for any n greater than 0, what I want to do is print n, then print all the numbers counting down from n minus 1. Printing is easy. We already know how to do that. How do we print all the numbers counting down from n minus 1? Well, we're defining an algorithm for countdown n, so to print the numbers starting with n minus 1, we can do this by calling countdown of n minus 1. Here's my recursive algorithm. The algorithm is called countdown, and it takes a single integer argument called the number. The base case is that if the number is less than or equal to 0, then I print a new line. Else, and here's the recursive case, and we know here that n must be greater than 0 because otherwise the base case would have caught it. So in the recursive case, I print the number, and then I call countdown of the number minus 1. I'm going to rearrange the algorithm a little bit to make it slightly cleaner by changing the order of the base case and the recursive case. Here's my cleaner algorithm, again called count down the number. I'll check the recursive case first. If the number is greater than 0, then I print the number and call countdown with the number -1. Else, in which case we know that n must be 0, I do a print line. Let's see how recursion works when an algorithm like this is executed. In this example, from the command line, I'll call countdown of 3. So first, it creates an activation record for countdown with n equals 3. And I'm going to show the position of the cursor on the screen here so that we can see the new line when it comes. Well, countdown of 3 tests to see if its argument, the number, is greater than 0. Well, it is greater than 0, so it's going to print the number and then call countdown of the number -1, which is countdown of 2. So it calls countdown of 2, and what we do first is check to see if the number is greater than 0. Well, 2 is greater than 0, so it's going to print the number 2 and then call countdown of 2 minus 1, which is 1. It calls countdown of 1. The first thing it's going to do is check to see if the number is greater than 0. Well, 1 is still greater than 0, so it's going to print 1, then call countdown of the number -1. It does that and calls countdown of 0. Now, this time, 0 is not greater than 0, so it's going to print line, and we can see that happen on our virtual screen up on the right upper side. And it's done. So it returns back to the copy of the algorithm that called it, and there's nothing more to do. So it returns to the copy of the algorithm that called it. There's nothing more to do. It returns to the copy of the algorithm that called it, which is our original copy. There's nothing more to do. And it returns. I'm going to try one more thing with countdown. Let's look again at the algorithm. If the number is greater than 0, then I print the number and call countdown with the number -1. Or if I've reached 0, then I call print line. I notice that in the recursive case, the algorithm prints the number and then calls the function with the decremented argument. That makes sense because we're counting down. For example, if the number is 4, the algorithm prints 4, then calls itself with the argument 3. So the algorithm prints 3, then 2, then 1. What would happen if I changed the order of the statements so that the algorithm first called itself with the decremented argument and then printed the number? In my example, the argument would call itself with 3 and then print 4. So we know that the 4 would be printed after the 3. What happens with the call to countdown 3? Well, similarly, the algorithm would call itself with the argument 2 and then print 3. So we know that the 3 would be printed after the 2. This means that if the recursive call comes before the print statement, what happens that instead of counting down, the algorithm counts up. As a result, I can rewrite countdown to create easily a recursive algorithm for count up. Here's count down. In the recursive case, I first print the number and then call countdown with the number -1. And by changing the order of the statements in the recursive case, I now have an algorithm for count up. My recursive algorithm for count up takes the number as its argument. The recursive case is that if the number is greater than 0, then I count up the number -1 and then print the number. My base case will be implicit. That is, I'm going to do nothing, just return. Otherwise, we'll print out the new line before printing the numbers. When I implement the algorithm in Java, I'll take care of the new line by putting it in the driver that calls countup. You might try tracing the activation records for countup to make sure that this algorithm does what I claim it does. Well, that's an introduction to recursive algorithms. Algorithms that call themselves to solve successively simpler problems until they reach a problem that they can solve immediately, which is the base case. I presented algorithms for arithmetic functions and algorithms for output procedures. In video 14.2, I'll implement all these algorithms in Java. See you shortly.